Thanks, Nick. Thank you all for stopping by. We're jumping from your first lecture with what was a regular, sort of traditional, conventional X-ray absorption spectroscopy to high-resolution methods. That's a leap, but don't worry, everything will be explained to you. So first of all, this is a new slide deck. I don't know how it's going to go in terms of time. I encourage you to ask questions, as I think I can always stop and discuss. And when when he throws a piece of fruit at me, I know it's my time to stop. This is how I'm going to structure this talk. I'm going to go back to like regular XES for a little bit because I don't know what your background is, but I needed to go further. I will talk about what high energy resolution spectroscopy is, how we do it, what's like the practical limitations of this method. I'll bring a few examples of each of those techniques because there's really a number of things that fall under this category. And if I'm not inclusive, if I didn't touch your field of study, I apologize. I come from material science. This is where, okay. So, all right. So what is XES? Okay, here we have X-rays. We have absorption because the photons are absorbed in your sample, and wonderful things happen after that. And then the spectroscopy, this is the word that means that we have to change something, change the energy or change them. In this case, the energy of X-ray photons in order to record this spectrum. And I'm going to focus on this field of hard XES because they are the gamma rays and tender and soft and UV and all do wonderful, wonderful things. We're going to talk about hard X-rays. And in terms of but the coverage of what we can measure, if you look at periodic table, it's kind of from titanium down. Everything that's down, we can look at and characterize. The basic physics of XES is that we have a certain energy state, a certain electron. And in case of the hard X-ray, it's usually the core electrons, the 1s or 2s electron. And then we get them out of the atom when they absorb X-rays. Right? Then what happens after that? Now you form something that's very, very not stable. Here in the core of the atom, you have a hole. And this, nature doesn't like that. So immediately, or almost immediately, we'll talk about this, there will be another electron falling down from the higher energy state. And this happens really fast. It happens within the femtoseconds. And we'll talk about why it's very important. Okay, a little bit of lingo I'm going to use for the slides. So as we scan the energy, at some point, we will hit that exact energy difference between the unoccupied state and the core state. And this is where the atom will start absorbing the X-rays. So less would come through and come at. And then this is where the absorption starts, this interactions between the electrons and unoccupied clouds. And then we'll get higher in energy and we'll hit the photons out of the atoms. And this is where the white line, and after this, then we're supposed to have a pretty steady absorption because all we do now, we just kick in the electron into continuum. But now there is this EXAS part, which is very, very important. I think I saw it on of the posters, where those modulations are actually telling us what's around these atoms, because this electron that comes out, it's a photoelectron, it's a wave, just like it's a particle, and it interacts with the outcome electron interacts with the electrons that are scattered by the, and you can get a lot of like short range as opposed to diffraction, short range structural information about the element of interest. All right, so let's talk a little bit about this process that happens after the absorption. So we kick the electron either to unoccupied states or into the continuum. So we form the hole in the core level. Now a few things can happen. One is that you have the 2p to 1s transition. And this is just because, well, it's not just because, but it's easy to see how this is the shortest distance, and this is the process that can happen with the highest probability. You'll see why it's important. The other process that can happen is that from the electron from 3p falls down and fills this hole. And this is what's called, so the first was K alpha emission lines, and those are K beta emission lines. Now, notice this multiplier here. This is actually much weaker than this. Now, there is a remote possibility, but very important possibility, that the transition happens with the electron from a 3D level. And I'll show you why. These photons that come out, emitting photons, it's called X-ray fluorescence. It's like visible fluorescence, just an X-ray region. And I mean, it's easy to see how those photons that come out that are lower energy than those that come in. And the width of those lines, the separation, I'm just looking at K alpha here, that's about 10 eV electron volts, and this is the unit for X-rays, and this is like several EVs wide. The detectors that we use, like in traditional XES, are semiconductor-based. And due to the characteristics of the semiconductors, the resolution, that is the ability to know exactly what the energy of the photon, incoming photon is limited. And the best case scenario, and I'm not going to go into why, is about 130 electron volts. So if we're looking at this line with this kind of a window, we're not going to see them resolve. We're going to see one big blob. Not cool. And they're even simpler detectors, very powerful detectors. They just don't see any energy discrimination, don't do any energy discrimination at all. So they would just give you the overall number, the integrated number of photons. Now, another problem with this, so that's one problem, that we cannot see those lines individually, and we really like to. The other problem lies with the traditional X-ray spectroscopy. The transition from we have the core hole to another electron filling that could be as short as a single femtosecond, so sometimes in a fraction of a femtosecond. And just like, you know, the momentum and position is connected, the uncertainty in momentum and uncertainty in position is connected by the Heisenberg uncertainty principle, so is the uncertainty in time and uncertainty in energy. That means we cannot define the energy of this state with high enough precision. And they say the quantum and real life, they don't really meet. I think it's actually a good metaphor for this, because if you're looking at something like, you know, something that happens very quick, it's probably you will not be able to understand what's exactly going on, as opposed to the situation where you're given some time to examine what you're looking at. So that's what's happening here. And this uncertainty in energy could be like a few electron volts. Nothing that precludes you from doing great science. But in the subsequent slides, you will see how we can deal with it. And how do we deal with it? We are using diffraction to do spectroscopy. And this is not the first time we're using diffraction. This is the second time we're using diffraction. Show you why. So basically what we want to do, we need a detector that is able to sample like very, very narrow energy. Okay? And we're doing it using crystal analyzers. And this would be, I mean, there's no scale here. I should have put it. It's about like 4 inches round thing, which is the silicon wafer or germanium wafer, polished and processed in a certain manner, or there are other kinds. But before I go into this, let's talk about the first time when we use X-ray diffraction. And for spectroscopy, we need to select and then modify the energy. As you remember the spectrum and the XES and XANES and all this, we need to scan the energy. And for X-rays, what works very well is crystals. Crystal lattice acts as diffraction lattice, right? So those rows of atoms, they would diffract the incoming X-ray light, and what comes out of synchrotron is sometimes it's a very broad spectrum of X-ray, sometimes it's narrow, but it's definitely not enough to do what we want to do in spectroscopy. So out of all this polychromatic light, we select a certain energy, and then we use the second crystal, which is a technicality, but very important technicality. We'll put it on the same beam path. So those need to be like very parallel. And the way how we select the energy is we move, and it's very, very easy to me to show with my hands, but this mechanism can cost $1 million to do it very precisely and very repeatedly. We rotate the two crystals around the where the beam hits the first one, and we change the energy. Could be done very precisely. And obviously, there's dynamic diffraction. John can talk about this, why we're not selecting just one energy, we're selecting a certain range, but it's good enough for us. Now, if we're at the synchrotron, we're working very hard on making the light, the beam, parallel or collimated before it hits the monochromator. We cannot afford this. We cannot do it with the fluorescence light. Your sample, once it's hit by the X-rays, it's a point source. It emits in all directions, not exactly in all directions, but in many directions. And instead of using flat optics, you're using curved optics. And this is the fit, and it's on right. You need to make very thin wafer, dice it, and then glue it to a substrate. It's expensive, but it is what it is. Now, again, just like with monochromator, we need to scan the energy because we want to be able to record emission line. Okay? And it's a very interesting motion. Right? The crystals, the detector, and the sample, they have to be on what's called the Roland circle. And as you move it, and your sample remains the same place, it's kind of funny how everything moves. And you need many motion, many motors, many degrees of freedom to realize the kind of thing. And I'll show you what it takes. Now, this is one way. You take the lights coming from your sample, You have this spherical analyzer that focuses this certain wavelengths, certain energy onto the detector, and you move the whole thing, and this is how you scan. But if you bend the crystal in only one direction, like cylindrical bend, what it would do, it would actually disperse the light onto a line. Sometimes it could be something else, but this point, the line where each pixel here on this detector would give you an emission, a different photons emission, a different energy. And they're good for different things. One works very well for dilute samples, but it's slow because you need to match the position of all these components. What's called the von Hammes, it's all German sounding names, and their papers from 1932. I cite sometimes. So Johann and von Hammes. So that works well for concentrated samples. It's very fast. So there are trade-offs. And we, for once at my beamline, we have two different spectrometers to satisfy the needs of most of our users. Okay, now this is how it looks in practice. The more crystals you have in your spectrometer, the higher your street cred within the community, right? And the kind of a good number for this is 5, right? So this is our five crystal spectrometers. This is a detector arm. The sample sits here. We rotate here and move. And then each crystal has 4 degrees of freedom. We have to move it left and right, up and down, and rotate it in 2 directions. So it's a really complicated motion that we need to, but we know how to do it. You don't have to care. It's just that sometimes when things go badly, something doesn't work, please understand. It's a complicated problem, and we're trying to help. All right? So your gateway drug into high energy resolution methods is the horrible acronym. High energy resolution fluorescence detector, XANES. HERFD-XANES. All right? How we do it? This is the least sophisticated technique, but very powerful. You set your energy of the analyzer to the maximum of your K alpha or K beta, depending on what you want. And what it does, it magically, not very magically, removes this core lifetime broadening due to a very short life of the excited state. And what's really, really boring, right? Platinum L3H, which is like every person in the catalytic world has done. Instead of this dull thing, you get a much, much sharper line. Now, this is probably not the best. This was like the first data set that we recorded. I'm very proud of it, so I keep showing. But it's actually not as showing as something that you will see in the rest of the talk. Okay. So one thing in the spectrum, in this diagram of the spectrum I wasn't talking about in much detail, is this pre-H region. So when you're scanning the spectrum, you hit all kind of transitions from 1s to 2p, 3d. Those transitions are actually not allowed per quantum mechanics. But nothing is strictly not allowed in quantum mechanics. There is a possibility that distortion, the more symmetry in the system you have, the less, the more not allowed. The more symmetric the system, the less the probability of to see those slides, the pre-H they're called. But they're telling a lot about the system. Symmetry, electronic structure, the geometry, which is another way to say symmetry, oxidation state. And from what looks like, just a blob with a little shoulder in the conventional XANES, we can get a much better definition. And where does it help? All right, so that's a real problem. We have a copper on zeolite on the catalytic reaction. What is the oxidation state in the in operand during the catalyst work? Okay, this is the signature of copper 1, right? It's very strong. Here, we cannot see anything in this blue conventional spectrum. This is the bow up of this region. This is a signature of copper 2. This tells us that in the active state, it's actually not one. It's a mixture of the two. Would we be able to resolve it? Here, if I stare at it for about 2 hours, I can discern the little inflection that will not go well with the reviewers, I'm sure. So that was an example from the catalysis. This is an example from environmental science. It has to do with microplastics. Microplastics, especially when left in the environment, they tend to absorb things. One of the first things that they absorb is iron, because iron is everywhere. And iron, in turn, promotes the absorption of really nasty things, such as heavy metals. And in order to understand this aging of plastics, you need to understand what the iron chemical form is. And again, I'm not showing the conventional data, but here, from just the form of this pre-age obtained by HERFD, one can identify the ferric species, which, again, the implication of the secondary absorption and also on the decomposition of those plastics, because there's a multitude of processes going on there. That's another example from catalysis, from electrocatalysis. The accuracy, the precision that HERFD gives you compared to the regular XES allowed those people to identify not just the chemical state of copper, which goes from copper 2 to copper 0 to metal, but also to the what size of clusters that they're forming. Now, there's one caveat here. The ability to analyze the high-resolution data relies on understanding the theory well. And like this poster shows, analyzing XANES is not an easy task. So you need to rely, in many cases, on theory or different levels of DFT and so on, of course. But that's okay. X-ray emission spectroscopy. This is the technique where we want to look at the emission lines, resolve emission lines. There we were still looking at absorption spectra, but with better resolution. Here we want to look at emission lines. Okay, so I'm just repeating here. This is two representations of what goes on. K alpha, K beta. This is a very interesting beast. It's called the valence to core transition. I'll tell you why it's so interesting in a moment. And this is a kind of real intensity ratio and the distance. And I also need to say that if you like, after this lecture, you're enlightened and go, oh, I really want to do this, but I think I need to do the K alpha measure. And then I will tell you, there is a certain cut of the silicon crystal, and I'm just throwing it out there. It's silicon 444 that works for this, right? They come to me and they say, okay, I want to do it. Say, okay, I have $25,000 for you to buy 5 crystals of 444. And then the following day, would be, oh, but K-beta would be so interesting. And then you come to me and say, look, I only have $25,000 for you. Sorry. So for oftentimes you can use the same crystal, the same cut for those two, but it would never be the same cut for this. So you need different crystals. And we have, I'm not showing it here, we have a library of probably 30 of those that we keep adding to this. Okay? So what is these lines are telling us? First of all, K alpha, K beta, they're split to 2. This is either because of spin orbit coupling or electron exchange interaction. They are actually sensitive to something you don't think, I don't think very often about, which is spin of the system. But it turns out, and I'll show you, how it translates into more tangible things such as oxidation state, things like that. All right, now this is a very powerful measurement. Why? If you think about core X-ray spectroscopy, it's not actually very smart to do it, because what you are after is chemistry, right? And chemistry happens in valence levels, very high in the energy. Whereas you're probing the core electrons, they're deep, very deep. They don't even interact very much. And still, there is the coupling that allows to tell you, oh, because this line shifted, even though it comes from the electron in the deep core, that tells you something about the oxidation state, which is the valence level proper. This is your microscope into the valence states. Those, if you look here, those comes from 3D electrons. And 3D electrons are hybridized with ligands. If you've done XES in your life, you would inevitably run into a problem. What is this next to my absorbing atom? Is it oxygen? Is it nitrogen? Because for XES, as long as the cross-section for scattering is the same, we cannot tell them apart. But because oxygen and nitrogen are very different electronically, they would affect how that is hybridized with the ligand and will change the spectrum. However, nothing comes for free. The most information is in this tiny little thing that sometimes takes us hours to collect to a desired quality. All right, so this is the example for 3 manganese oxide, 2, 4, and 6. See, here we have a slight shift. Here we have quite a big change in B prime, but here looks very, very different. And there's theory to this of why that happens. All right, so this is another way to show it. Here's this transition, orbital 3D. It's hybridized with 2p. And the transition that you see is beta 2.5. And this terminology goes back like 80 years. Nobody understands why they were calling it this, but we keep on going. So one is from 2s of the ligand and another from this hybridized state. And that gives you a window not only into the nature of this atom, whether it's nitrogen or something else, but also in the charge. One is oxygen here, and one is hydroxyl, and is quite a big difference. This here is titanium foil, titanium nitride, and titanium what is it, iron titanate. And again, there's dramatic changes, even though here you have nitrogens in the first coordination sphere, there you have oxygen. So very sensitive technique. I'm going to skip on this one. But with the valence to core is on top of everything that I've said. It's actually the direct measure of the density of states, something you can get with XPS. With XPS, you need vacuum, not compatible with some of random measurements. So here you get pretty much the same information from XPS, but you can do it in air or in a reactor or whatever you like. This is an example from catalysis field, selective catalytic reduction of NOx. For some reason, this catalyst works well at 150 degrees in the presence of water, but not at higher temperatures. And you see, you can add water or not add water, the spectra hardly change. Here at 150, it does change. And this is actually the evidence of there is a flat iron complex, and this iron comes out of the plane, and its ability to bind the reactants goes down, which means that it accelerates the reaction. And also here in the valence to core loop, this is a horrible spectrum, but it is what it is. You have this new line that only happens when you have the NO and ammonia, the right combination of the material of reactants to get the reaction going. So that's direct evidence for the intermediates. More examples. I mean, you see difference in spin, and this difference in spin translate into the structure. This is electrochemical reaction, which employs a molecule that looks like this. Again, it changes the where it's located within the ring as the potential change, and makes it an active catalyst. 2 slides about fancier measurements. Now, if you have the ability to scan the incident energy with a monochromator, actually, and you have the ability to scan the fluorescence energy with high precision, that makes it very powerful for electronic structure determination. And I just want to, so basically now you have 2 variables, so you can build the map. And this is what's called the RIXS, resonant inelastic X-ray scattering. Instead of, and we are looking here, believe me, you're looking at this area. You see those little bumps here? It's worth remembering that the XES spectrum is a projection of the of this RIXS map onto this axis. So you just integrate it like this. So here you will get a bump. Here you will get a bump, or 2 bumps. But now this is the cobalt 2 and cobalt 3. You have a much more sensitive probe to the electronic structure. I'm not going to go into details. Another method is the X-ray Raman scattering. Just like in normal scattering, normal optical Raman scattering, you have the incident photon, hits the atom, it scatters, but it's not scattering elastically, it scatters through this mechanism where some portion of the energy is transferred to the inner shell electrons. And what you can do with this is you can measure the spectra of light elements that would typically require soft X-rays, and ultra high vacuum conditions. This is a terrible technique. This spectrum I'm showing you, it has taken days to collect because the cross section for Raman scattering is very, very low compared to everything else I was telling you about. But this is a very interesting, I think it's worth an anecdote. So someone, if you were doing even ex situ, XES measurements, you would know that to adjust the amount of material, you will use a dilutant. A very popular dilutant is boron nitride. And this is what someone tried to do in a catalytic reactor. They diluted their catalyst with boron nitride, and they ran dehydrogenation of olefins. I don't remember what it was. The activity was higher than the catalyst itself. Turns out, accidentally on purpose, boron nitride is active in this reaction. And it's from 2003. So a recent work from Stanford where they actually measured the boron chemical state in this reaction. And again, there's what happens is there is delamination in this material, there's activation, there's oxygen, and okay, so I have how much? 344. Okay, I'm just going to tell you a few things of like practical things. This experiment is slow, right? Because you need to move all those degrees of all those motors. They're like, oh no, not 2.3, 23 motors that need to happen in coordinated fashion. I apologize. Now, because we use the certain geometry, there's the collection of the crystals, how many photons, is very, very small. So the experiments are usually considerably longer. Another consideration is that not too many places have those capabilities. There are only like 4 beamlines in the United States or in North America, for that matter. So typically you need the beamline, but I have to say that they are now benchtop instruments that can do this. They cannot compete in terms of the throughput, but it is still very powerful. As far as the sample environments go, pretty much everything that's compatible with regular X-ray spectroscopy would work for this. Sometimes you need to think, because those crystals crystal array could become very large, and you won't be able to use all of them. But traditional catalytic reactors, electrochemical cells, and battery cells, they're all good. They all can be used. Okay, I'll stop here. I have a story, which will probably take me 5 minutes to say. Okay, and this is actually, and I just I gave a sciencey talk about this, and it's based on the work of our collaborators and done at ESRF. We're now working with them closely, but all this data is, most of this data is from the previous work. And this concerns mercury. This is dear to my heart because, well, I like sushi. And there was another reason that I forgot. Anyway, so mercury. Mercury is everywhere, as you know. Mercury was known for a very long time. The most, one of the most important minerals that contains mercury is cinnabar. It was known to native tribes in America for a very long time. They used it to trade it, to paint their bodies. And they come from both natural sources and human anthropogenic sources, because there's plenty of mercury in coal, and we'll now start to burn it again, I guess. So, in many animals, typically apex predators, have the ability to store quite a lot of mercury in their bodies. And this is those guys, these really big guys. So if you look at the amount of mercury in different tissues, and that was the other reason. That was the coolest sample that we had, I think, so far. This was a dolphin liver. So you see how you can get into very high dose very quickly if you eat sushi. Or sashimi for that matter. All right, so that's so the question is, how can they tolerate this high level of mercury without dying? And they probably have a way to neutralize this. But let's talk about the kinds of mercury first. There is elemental mercury, you know, the broken thermometer from 1965. They can affect a lot of organs, but that's bad. But so bad. Mercury salts, they're not very good to you either. They act upon your guts. The worst perpetrator is organic mercury, methyl mercury. And it actually comes from the bottom of the ocean, from the bacteria. They produce it there. It's soluble in lipids. Why is it so bad? It's soluble in lipids that can penetrate the blood-brain barrier, end up in your brain, and lead to all kinds of neurological conditions. Now, what it does, remember how cinnabar is a mercury and sulfur? Mercury can bond to the cysteine, one of the essential amino acids, and essentially change the structure of the protein. So this is how the mercury spectra look like. Those are different. The metal, sulfide, oxide, acetate. It's really boring, guys. It's really featureless. However, with HERFD, we can sharpen all those features. So it goes from looking like this to look like that, right? That's a cute little bird from like California and the west coast of Mexico, Clark greb, that we looked at. Different tissues will have different composition of mercury in them, different chemical states of mercury. This is methyl mercury, very toxic. But if we have a kidney, this guy, or a liver, the spectrum would look substantially different. Whereas in the brain and feathers, it would look like this nasty stuff. And we know that liver and kidney, they know how to metabolize mercury. And it's actually what the analysis was telling us, again, something that we would not be able to do with a structureless traditional XES. They tell us what it's bound to selenium. And selenium is an interesting, so mercury was known for, 3,000 years, was used in Chinese medicine. Selenium was discovered relatively recently by chemistry term. And mercury was used in many, many things. And so was selenium. They first recognized this poison because as they did, the researcher who discovered this, he decided to eat it. And he didn't like it. And then they decided it's a poison, only to find out about 100 years later that micrograms, I actually don't know what the right level is, but as the micronutrient, it's absolutely essential. All right? And if you think about where it is, it's just under the sulfur in the periodic table. And as people started to look, they started to look at the structure of the selenium-containing proteins, which are not very many in the body, but they exist. It turns out that those selenium-containing proteins can capture the mercury in this site with 4 selenium. And this is how it works. This is how it neutralizes, how those proteins in a certain tissues in the animal bodies would neutralize those poisons. So just one last message. If you're in Florida and if you caught a Burmese python, don't eat it. It's an excellent mercury bioaccumulator. Okay? Thank you.